Welcome to The Explainer. Today, we are exploring a really fascinating three-part ARRL laboratory series written by George Spatta. We're going to be revealing the unseen microscopic battles that are constantly happening right inside your radio receiver every time you tune into the high-frequency or HF bands. Okay, let's dive right into this. Have you ever been tuning the dial and suddenly heard this ghostly CW station bleeding into the voice part of the band? Or, maybe you've had a faint signal completely vanish into thin air just because a strong station fired up nearby? It always seems to happen right when you're about to finally log that rare contact you've been chasing all week, right? Well, today we're going to diagnose those exact real-world frustrations. We're looking at why ghost signals appear, why faint signals just unexpectedly fade away, and the causes of that super annoying audible pumping when strong broadcast stations operate dangerously close to your frequency. To do this, we're basically going to treat your radio receiver like a patient on a diagnostic journey. First, we'll define what a healthy baseline receiver actually looks like. Then we'll identify 3 distinct diseases that aggressively attack it. And finally, we'll prescribe the cure to keep you operating smoothly. So here is our diagnostic roadmap for today. 1. The baseline. 2. Reciprocal mixing, or RMDR. 3. Blocking, or BDR. 4. Third-order IMD, or DR3. And finally, 5. Practical fixes. Section 1. The baseline. To properly diagnose a radio, we really have to first understand the healthy baseline of how receivers manage crowded, noisy environments. The absolutely crucial metric here is dynamic range, which is often just called DR. Now, dynamic range is the critical gap between the absolute strongest signal a receiver can handle without creating nasty audio artifacts and its baseline sensitivity. That absolute bottom floor of sensitivity, by the way, is known as the minimum discernible signal, or MDS. To find this baseline, the ARRL lab rigorously tests equipment by actually injecting multiple simultaneous test signals into the receiver. This effectively simulates real-world conditions, like exactly what you'd experience on a heavily crowded contest band. This dynamic range gap is your true operational window. It's literally the space where your radio functions as intended, allowing you to clearly hear what's on the air without the radio buckling under the pressure. Section 2. Reciprocal mixing noise, or RMDR. Let's move to our first culprit attacking that precious dynamic range, reciprocal mixing. Imagine a perfectly clean local oscillator with a sharp, narrow signal, and contrast that with an oscillator suffering from poor phase noise, where the signal spreads out like a wide skirt. Why does this even happen? Well, internal oscillators just aren't perfect. They suffer from microscopic timing jitters that translate into this messy phase noise. When you tune your radio, this local oscillator's composite noise actively mixes with strong incoming signals from nearby frequencies. This dangerous mixing actively raises the receiver's noise floor, essentially burying weak signals in a broad spread of noise sidebands. It's exactly like throwing a thick, heavy blanket of static over that faint station you are desperately trying to hear. Let's put the math behind this masking effect into perspective for a second. Think about 72 decibels. If a strong station nearby is 72 decibels stronger than a faint CW signal you are straining to hear, a receiver with poor RMDR will let that strong signal's phase noise entirely mask your desired contact. The crazy part is, the band itself might actually be perfectly quiet, but your radio's internal noise makes it literally deaf to the weak signal. It's completely a self-inflicted wound by the receiver's own internal architecture. Section 3. Blocking dynamic range, or BDR. But what if the noise floor isn't rising at all, but your desired signal just suddenly gets quieter? Well, enter our second villain, blocking dynamic range. We need to make a really clear distinction here. While RMDR raises the noise floor, blocking acts in a completely different way. It acts like an unwanted, invisible automatic volume knob. When a massive signal appears nearby, it physically saturates your receiver's front-end amplifier. The front end simply runs out of headroom to process all those incoming electrons. This forces the radio into compression, physically lowering the gain of your desired signal. So the noise doesn't drown your signal out. Rather, the radio literally turns a deaf ear to it because its circuits are choked by the overload. Section 4. Third-order intermodulation, or DR3. Our third and final culprit is third-order intermodulation distortion. This is the specific disease responsible for those garbled voices and ghostly stations. When 2 or more strong signals pass through a nonlinear circuit element in your radio, like a mixer, they don't just pass through cleanly side by side. They actually interact and modulate each other. As these signals mix in a nonlinear environment, they spawn new frequencies. This generates entirely new, undesired intermodulation products right out of thin air. These phantom signals can plop right down on top of the exact frequency where you were trying to copy a weak signal, completely masking it with a ghost broadcast that doesn't actually exist anywhere on the real band. And the terrifying math behind DR3 is based on a Taylor series mathematical model. These third-order intermodulation products don't just grow linearly alongside the interference. They actually increase up to 3 times faster than the desired signals. This 3-to-1 slope means a tiny 1 decibel increase in incoming interference rapidly creates a massive 3 decibel change in these generated ghost signals. If the interfering signals get just a little bit stronger, your radio essentially starts fabricating its own incredibly crowded, messy band, completely overpowering anything you actually want to hear. Now, we should definitely note that modern software-defined radios, or SDRs, handle this third-order distortion quite differently. Instead of that classic, predictable 3-to-1 slope we just talked about, the analog-to-digital converters and SDRs can exhibit unpredictable, roller coaster-like distortion as signal levels rise. Eventually, they hit an absolute clipping point that produces harsh, broadband noise rather than those discrete ghost signals. To counter this, SDR manufacturers often use a technique called dither. Adding dither essentially means injecting low-level random noise directly into the signal. Take a second to appreciate the irony there, adding noise to fix a noise problem. But it actually smooths out the quantization errors, allowing the SDR to operate smoothly, even though it is fundamentally different from traditional analog overload. Section 5. Practical fixes for operators. Now that we've diagnosed all these issues, when do these metrics actually matter out in the real world? Well, HF band noise varies drastically by frequency. Dynamic range metrics matter way more on quiet bands like 10, 15, and 20 meters, where the atmospheric noise floor is incredibly low. Here, you will absolutely hear your receiver's internal flaws. Conversely, atmospheric static mostly masks these flaws on noisy bands like 80 and 160 meters. This is absolutely critical for dedicated DXers like Kim Stenson, who is mentioned in our sources. He spent 23 years chasing 300 countries on limited attic antennas. When he's hunting a rare entity like Crozet Island on 20 meters, he desperately needs a receiver that doesn't buckle and fabricate internal noise the second a strong adjacent signal appears. So, how do we fix it? The most counterintuitive but wildly effective fix for blocking is turning on an attenuator. Yes, dropping the signal. The secret to hearing a weak signal better is sometimes to make your radio deafer on purpose. This brings the receiver out of gain compression and back into its linear region, magically making the weak signal copyable again by preventing the front end from choking. You should also operate with narrower bandwidth filters to exclude off-frequency signals, physically check for loose coaxial connections which can cause external intermodulation, and when shopping for gear, prioritize choosing a receiver with a DR3 of greater than 90 decibels. Former ARL lab manager Ed Hare sums this whole thing up perfectly. He said, "The best receivers are the ones that don't make up signals on their own." A high-quality receiver is ultimately defined by its ability to simply report what's actually there on the antenna without adding its own phase noise, volume compression, or phantom ghost signals. It's all about preserving the pristine purity of the raw RF environment. Understanding the invisible metrics of RMDR, BDR, and DR3 really changes everything about how you tune your dial. So the very next time a faint, rare signal suddenly vanishes into the static, you have to ask yourself, is the band actually changing, or what's really happening inside your radio? Thanks for joining me on this explainer, and happy hunting on the bands.